In the next few slides, we're going to talk about this illustration. So it has part A and part B. In part A, this guy is throwing something up. He's at the edge of a cliff. He throws it up, straight up. We're pretending it goes straight up and comes straight down and magically goes over the edge of the cliff. All right, little pretend. So he throws it up at 13 meters per second. And we're going to be talking about how high it goes and then how fast it's going when it comes past him and it's tripped down to the bottom of the cliff. In part B, we'll also talk about that. In part B, he's throwing it down at 13 meters per second, right? So its velocity in part B is minus 13 meters per second. So let's talk about these two parts. The acceleration of gravity is a constant, we'll call it. I mean, it's relatively, in most of your experience, it's going to be a constant. If you launch satellites, it's not, because as you get further from the Earth, you have less gravity. Gravity is not even constant on the surface of the Earth. Here in the Mississippi Delta, gravity is more like 9.75, 9.76, something like that. Influenced mostly by the fact that in areas where you have lots of iron, gravity tends to be a little higher because the density of iron. We don't really have any iron here underneath us in the Mississippi Delta, and so gravity, the acceleration of gravity is just a little bit less. I use G, the acceleration of gravity, as a positive 9.8, and that means the actual acceleration due to gravity in a problem is minus G, so minus 9.8 meters per second. And that's because we're going to consider up to be positive direction. All right, that's our convention. You can rework it with down as a positive direction, but we're going to go with up as the positive direction. In the picture, right, where the guy's throwing this, y naught is 0, t naught is 0, v naught is 13 meters per second, and acceleration is minus 9.8 meters per second squared. Now, the equations for displacement and acceleration are the same in x and y. All we do is we change the variable names because we think of x as horizontal by our math conventions and we think of y as vertical by our math conventions. And so the equation for where this rock is that this guy is throwing, just you go to the equation we had before and you're just going to stick in minus 9.8 is the acceleration, 13 meters per second as the initial velocity, and 0 is y naught, the initial displacement. In part B of the picture, it's very similar. The only change is to the initial velocity, minus 13 meters per second instead of plus 13 meters per second. Does that all kind of make sense? All right, let's back up. Let's take a look at it. We're talking about this problem where the guy throws the rock up and it goes down. All right? And then we're talking about a second problem where he just simply throws it down. And if you look at how all of that fits into the equations, we have our acceleration, we have our initial quantities y naught and t naught. We simply stick it into the equation minus 1/2 times 9.8 meters per second squared times t squared plus 13 meters per second t plus 0 meters. In the situation where he's throwing it down, the only change is to the initial velocity. Instead of being plus 13 meters per second, it's minus 13 meters per second.